We were looking into filters. We last time did something about Butterworth. Butterworth is a polynomial which is given by a function b square omega, which is equal to 1 plus zeta square omega by omega 0 to the power 2n, and hence they called the order of Butterworth, order of polynomial. Now the idea in filtering is that since you are looking for a typical pass band, stop band, ripples, these functions which are mathematical functions, they can actually fit to the required desired response by proper choice of order of the functions. The Butterworth functions are also called maximally flat filters. Essentially they mean their ripples are extremely small. Okay. We last time were doing something about this. So I just thought I will repeat where I started, and I did derive out expression that a Butterworth function, normalized Butterworth function, can be written as 20 log 1 upon epsilon square omega omega zor, where this epsilon or zeta, whatever it is a function of ripple frequencies. So obviously larger n means larger attenuation. So one can see from this transfer function, if I want to attenuate sharp, larger the n number I create, larger will be fall in the from output to the higher value to the lower value. And I already shown you, as I increase the Butterworth polynomial order, n is equal to 1, 2, 3, 4, 5, 6, 7, the sharper fall starts. Okay. Now this essentially means if you are looking for a very great sharp filters, also you need a very low ripple, you may have to require 7 stages. N is the number of stages or sections, each n is a pole, each n will give you a pole. So each section will have one circuit which will realize a pole, and if you have larger number of poles, those many sections you will have to create. So if I see, for example, for 7, one can see it's a very sharp filtering has been done. This is for a low pass, similar thing can be done for high pass. So a sharper fall essentially means larger value of the function you are creating, or n being larger, and that is the problem. So and as I said last time, larger the n value, larger is the issue of money, and therefore the cost wise it is better if your n number is relatively smaller. So I will give an example to solve my problem. Let us say this is a attenuation function. Please remember Hj0 by H0 is the attenuating function, maximum value is 1 and it will start going down, that means it start attenuating higher and higher, and you can see larger n will attenuate at lower frequencies, means sharper bands. Okay. And also you can see the flatness of the curves, okay, in the pass band. Ideally what is the low pass filter response I am looking? I am looking as if something like this. This is an ideal low pass filter response, and I am trying to replicate it by using a polynomial function which fits closer to this. All that we are trying to fit the function as close to that, and doing so we figured out that larger than I put, closer I will come to the reality. Okay. What normally I said you other day, there will be a ripple, okay, and then there is some kind of a fall which is a transition band. So I want to reduce transition band, I want to reduce the ripple, I want sharper falls. So I require larger polynomial functions. Larger number means, as I said, each n will give you, as we shall show you the function, each n will give one pole. Larger the number of poles you create, one can understand why larger will fall faster. Each is 20 dB, 20 dB, 20 dB, say 7 poles, 140 dB it will go down. Okay. So the trick of the trade is how many sections you can tolerate by your money in your pocket. Okay. So this is the Butterworth function, and one can see from here, if you are noted down, I will just show you. Okay. Here the Hs is a transfer function which is nothing but V0 by Vns, which has to be a As by Bs, and if it has only poles or no zeros, it is called all pole transfer function. There can be zeros, but we normally want to have all pole transfer functions. Then Hs, let us say there are no zeros, so As is never at except at omega equal to 0 it is a pole probability 0, but otherwise it is H0 upon Bs, and the function which is called Butterworth polynomial is given by b square omega is 1 plus zeta square or epsilon square omega by omega 0 by 2n, where omega 0 is the cutoff frequency at which you want first pole to occur. Okay. Epsilon is a I won't say constant, say variable, or rather you may say for the particular polymer it's a constant which is a function of ripple frequency. It's some function which has, we will actually evaluate that value of how much it should be, or normally they may give, zeta is typically taken 1, zeta is typically taken 1 in the case of Butterworth polynomial. Sharper this, zeta is taken 1 in Butterworth, but zeta will be taken something else in case of the other filters which is Chebyshev. Okay. So unless assumed, unless not critically specified, use always epsilon or zeta whatever you feel as equal to 1, okay, unless stated otherwise. Okay. So this is the Butterworth function, and what I am trying to do, I want to fit this kind of function into the pole 0 functions, and I will like to see whether it replicates the desired response. This is all that I do when I say I am designing a low pass filter, or for that matter any filter. If I calculate h omega function as I gave you there, it is h0 upon 1 upon epsilon square omega by omega 0 to the power 2n. At omega equal to omega 0, hj omega 0 is h square upon epsilon square, and normally as I say epsilon is treated 1 most cases. Hj omega 0 square by h0 is half. So this epsilon, if you want the value, it is 10 to the power a by 10 minus 1, a is the actual gain h0, it should have been h0 there. So the maximum transmission A max occur at this value, and therefore epsilon value I can calculate, but typically as I say I choose a value of 1, so this function goes to a value of half. A max is it's a hj0 by h0 magnitude of that. Okay. It's a normalized gain function, so I named separately for that. Okay. Is that correct? hj0 by h0 magnitude of that is 20 log of that is this. Okay. So this epsilon is essentially something to relate with maximally flat conditions. And maximally flat conditions means what? The gain which I have already shown the figure, as flat instead of ripple, as flat as I get a response here, that is what I say maximally flat, because ideally what do I want? Sharp constant gain and fall. So as close I choose epsilon, I can get more and more flatness, but normally the maximum value which all filter people use is epsilon is equal to 1. Okay, I will give an example, and I think that all things which you have worried will be very clear now. Okay, here is an example which is very easy to understand. Let us say I want to design a low pass filter using Butterworth functions, and we want an attenuation of 40 dB at frequency of omega equal to omega by omega 0 equal to 2. Is that clear? I am giving an attenuation at omega twice the omega 0 is the first cutoff. Is that point clear? Which value I am talking? If this is my omega 0, twice this frequency, what is the value, transfer function value goes down? Okay, that value I say is 40 dB down it should go by. When the frequency doubles from the cutoff, I want how much attenuation? 40 dB attenuation I want. Okay, and we, as I say, I use epsilon 1. So if I write Butterworth function hj0 by h square is equal to 1 plus omega 0 to the power n, and since I am given hj0 by h0 is 1 upon 100, is that okay? Why 1 upon 100? 40 dB is 1 upon 100 magnitude, and that is equal to 0.01. If I substitute here in this function hj0 hj omega upon h0 square, I put 10 to the power minus 2 square, 10 to the power minus 4 equal to 1 upon omega by omega 0 is 2, so 2 to the power 2n. Evaluate. What I am going evaluation? What is that I am doing from this? What the value I am calculating? Order of polynomial, which will give me at twice the frequency from the cutoff, the attenuation by 40 dB. Okay. So I calculate n from this value, and this is equal to around 6.64, so roughly 7. So if I have a 7 section polynomial or 7th order polynomial, then what is the output of a filter will be that it will have a cutoff of omega 0, and at twice that frequency the attenuation will be 40 dB. That means it will fall 40 dB down by double the frequency. Is that clear? This means, so now you can see from here, if I want even more attenuation, what will happen? Let us say 60 dB. This n will further increase, 7 may become 12, 11, 10, whatever number it comes. So larger the attenuation you are expecting at a smaller frequency shifts, you can say omega equal to omega 0 itself, that value occur, it will be even n may be even more. Okay. At that point, if I want very sharp at omega 0 itself, then it will be even larger n number will appear in the real life, and that means what is the problem with larger n? So many poles you will have to realize, each pole will be realized by one section as we say, so many sections will be required. So you have a large low pass filter actually creating a relatively not great filter response. Okay. Because most cases you are not really looking for ideal low pass. Okay. If you are really looking for very ideal low pass, yes, all that we say 3 dB down, if this starts falling, it's fair enough. The problem starts, how much is that transition band you should allow? Okay, and therefore that is where the next, when it starts again, because if you don't reduce transition band, then the next filtering frequency will also come immediately. So we want to separate the pass band from the stop band. Okay, so I want to, as sharply I do it, that is what I am trying to look at. Okay. Now I have shown you one method of designing a filter by using a Butterworth polynomial. Okay. Now what is the problem? I said everything is fine, ripples are almost close to 0, but larger number of sections are required. Here is another function which does similar job and is called Chebyshev. Okay. Okay, so here is another transfer function which, or polynomial, which can create a transfer function which will also do attenuation. The only problem with this transfer function is that it will have a ripple. Okay. The typical Chebyshev transfer function can be represented as, and it has two possibilities, when the frequency is less than omega 0 and the frequency is larger than omega 0, the transfer function has this kind of expression, 1 upon epsilon square cos square. This Cn is a name given to Chebyshev function. This is my Chebyshev function. Okay. This is cos square n bracket n cos minus omega by omega 0 is the Chebyshev function. Okay. And this becomes, can you tell why cos become cos h? कोई सोच सकता है कि cos और cos h में फर्क क्या है? e to the power j5 minus e to the power plus e to the power minus j5 by 2 is cos, and if by 2j in case of sines. Okay, and if you remove that j's, then it will become cos h functions. So whenever the function is larger than this, according to this theory, the function becomes cos h kinds. Okay, this is how the functions have been. This function has nothing to do with filters per se. This is a mathematical function which was used by filter theory by Mr. Chebyshev. Okay, this is not, he only actually got this kind of function. So how do you get new functions? You have a lot of mathematical functions available. Okay, you try to see which one comes closer to the kind of actual response you are looking for. Okay, and then many times in engineering what we do, we put a fitting function on that. So, like for example, I told you, you give me any conic section, I can always put any order of polynomial in it, a0 plus a1x plus a to the some millions I can do, but everything can be fitted. I will get the coefficients, so I need so many terms to evaluate, so many coefficients to evaluate, but the end of the day, I can fit any kind of shape, any random shape. Conic of course is the relatively periodic shapes, but even any kind of shapes. This idea is therefore valid. After all, you are looking for some kind of this response, so you know initially it should be constant and then should fall, okay, or initially it should start rising and then become constant. So we are looking for some kind of a function. So easiest function क्या होता है, ऐसा rise करना है तो अभी ये exponential है जैसा, इसका time constant adjust करो, okay. So essentially even an exponential function, which is at why cos and cos h are appearing, because it's an exponential function trying to fit something, okay. So any mathematical function which tries to replicate the response you are looking for can be used, but these two became very popular because these can be implemented on a circuit much easier way. Why only these two? Because they were very easily implementable on circuit performance, which we have blocks like op amps, resistor capacitors. Using this, many of them can be easily implemented. Therefore, these two became extremely popular. But I am not saying there cannot be any other function better or worse than that. Okay, there can be many other functions. These two became only popular. Some other day will say, okay, there are other kinds of function also fits in and maybe fits in better at some other cost. Okay. But for this course, let's take it that these are the only two filters. So if I have this Chebyshev filter, and it is always said all Chebyshev filters are all pole functions, okay, there are no zeros in that, okay. However, they always cost you on ripple. The ripple of all Chebyshev filter is larger compared to Butterworth. Butterworth is called maximally flat, okay. In the Chebyshev there is going to be a ripple. But as in Butterworth, sharper fall for lower number of sections probably if you can get compared to Butterworth at the cost of ripple, then you are doing something better one way, other something you are losing other way. Is that point clear? I can reduce either the ripple or I can reduce the sharper fall. So if I say a very sharp fall, then I know I am going to increase my ripples, okay. If I want relatively lower falls, a sharper, lower sharpness, then I may reduce the ripple itself. That ripple is essentially given by what we call epsilon term, and it is related to a ripple whatever equivalent to in ripple gamma in dBs by this function. Epsilon square is 10 to the power gamma by 10 minus 1. This is the expression given by Chebyshev, no proofs needed. Epsilon square is 10 to the power gamma by 10 minus 1, okay, minus is outside. So we say if gamma is half dB, if the ripple is half dB, is that clear? Earlier in the Butterworth, how much epsilon or gamma, zeta value I chose? 1 only. Now I say depending on the gamma, I can choose different epsilon values. Is that correct? Depending on gamma value I choose, I can substitute gamma half dB, 3/4 dB, 1 dB, whatever ripple you can tolerate, you substitute here that though many dBs and evaluate epsilon. So for two cases, which is the most popular case in Chebyshev filters, one is half dB ripple, the other is 1 dB ripple, for which epsilon is 0.3493 for the first case and epsilon is 0.5089. This is just maths, nothing great, and these values are also not evaluated by me, I am just giving from Cedar Smith's book, okay. Hopefully their maths is also correct, because they also copied from Chebyshev's first paper. So hopefully Chebyshev was right, okay. But it's very simple maths, so you can verify on a calculator in a few minutes time. I have not done it this case, so please, I don't want to vouch on that, but must be right, yes. For the same 40 dBs, let's say, at the same frequency, if I get Chebyshev filter which is n lower than this, then I have achieved my part at the cost of ripple. Is that point what I said? I'll give the example. I'll use the same 40 dB fall at double the frequency, okay, and I say the sections which I get, how many? Are they less than the Butterworth? If they, yes, I have achieved, but what cost I am paying? This is either half dB or 1 dB ripple I am pro, which in the case of Butterworth I have no ripple there. So if you are really looking only flat bands, okay, then you require larger N to use Butterworths. I agree. Section is a one pole realization. What section word I am using? N is one pole. 7 poles आपको realize करना है. मैं आपको भी वो expression दिखाऊंगा तो आपको clear हो जाएगा. मैंने अभी तक शेबेशायर फंक्शन का actual realization expression नहीं दिखा है, मैं आपको अभी दिखा दूंगा. Okay, you have a point, but let's wait for it. So is that value I can calculate epsilon for any dB ripple, whichever you are asking. और आपने देखा होगा कि लार्जर डीबी के लिए एप्सिलॉन ज्यादा है, तो उस एक्सप्रेशन में आपको क्या फायदा होगा यदि एप्सिलॉन ज्यादा हुआ तो? वो जो शेबेशायर फंक्शन है ये ज्यादा हुआ तो क्या फायदा होगा? ये ज्यादा फॉल फास्टर हो जाएगा. इज दैट पॉइंट क्लियर टू यू? इज दैट पॉइंट क्लियर? इफ एप्सिलॉन इज लार्जर, डिनोमिनेटर इज लार्जर, द डीबीज विल बी शार्पर फॉल्स. इज दैट करेक्ट? सो 1 dB यदि रिपल ले रहे हैं तो आपको फॉल जल्दी मिलेगा, ये नेचुरल है. ये उसका खेल है. कितने सेक्शन जानना चाहते हैं? ओके, द रिपल फ्रीक्वेंसी ओमेगा सी विच इज ऑल्सो रिलेटेड टू 3 dB पॉइंट. अभी आप लिख लो, एक 3 dB फ्रीक्वेंसी मीन्स योर पोल. ओमेगा 0 लिखना चाहिए था, बट सिंस ओके कॉल इट ओमेगा सी और ओमेगा 0 में भी. ओके, तो नो सो रिपल फ्रीक्वेंसी ओमेगा सी है और ओमेगा एच जो है वो आपका ये है ओमेगा सी. सॉरी, जो कट ऑफ फ्रीक्वेंसी है, प्लीज रिमेंबर वेयर इज द रिपल कमिंग. अगेन वे लेट्स लुक एट इट. दिस इज माय गुड बैंड, दिस इज व्हाट आई एम गोइंग टू गेट, एंड एट दिस फ्रीक्वेंसी 3 dB पॉइंट, दिस इज रिलेटेड हाउ? Is that correct? This is 3 dB point, that is our actual bandwidth up to which passband exists, okay, and this is the ripple frequency. So this ripple frequency is related by Shebesh function to this corner frequency by this expression. As I said, the function has, when I have used the transfer function which I have given you, I start increasing omega from say 0 onwards. So initially, because of the function of cos is varying function, it starts rippling, okay. At omega equal to omega 0 or omega h whatever 3 dB point, we say the transfer function net value suddenly starts falling because of the other n e to the power n values which I have given. As it starts falling, I say ripple at that corner, whatever is the ripple available, I want to make relationship with this corner frequency to the ripple frequency. Essentially, ripple is also not one frequency term, it is a multiple frequency term, but the fundamental of that ripple is chosen as the ripple frequency. Whatever is the ripple frequency at that point, that I am related to the corner frequency by this expression which is from Shebesh theory, okay. Right now assume, as I say, I am not doing Shebesh functions because it will take longer time for me. Your next course you should hit them, okay. The cutoff frequency, 3 dB cutoff frequency is related to the ripple frequency. Ripple is, as I say, ripple is not constant, it is like this, like this. इसका जो fundamental frequency है उसको ripple बोलते हैं, और ripple frequency it has the largest component among all other frequency terms. That frequency to the corner frequency का relation ये है. Okay, so let's take the same example. I have a 1 dB ripple accepted, n is 5, this is 1.03 relation है इन दोनों में, okay. What does this mean? Omega c and omega ripple frequency is 1.03. क्या meaning है? If the cutoff frequency and the frequency of the ripple is very close to each other, what is the advantage you will get? When you substitute in this, the h function will start falling sharper at that point, okay. As close you come to the, that means ripple is इसका कितना, ये जो फ्रीक्वेंसी है इसमें भी इसका भी फ्रीक्वेंसी वही है, इसका क्या मतलब है कि ये ऐसा ही है एक्चुअली. There is a very little other frequency components going through. So it is almost becoming average value is very close to the maximally flat value, average value. That's what we are looking for. The frequency of fundamental should be such that its average value is close to flat value. Is that correct? उसका amplitude इतना कम हो कि वो flat value के करीब आए. This is what Shebesha is trying. So I calculate for 1 dB. Let's say same example. Is that clear? What was the last example? 40 dB down at twice the cutoff frequency. We want twice the frequency, attenuation is 40 dB, and now I am saying ripple is 1 dB. 1 dB के रिपल के लिए एप्सिलॉन का वैल्यू 0.5089 था, इसमें सब्स्टिट्यूट करो और ये आपका शेबेशायर फंक्शन है Cn square by 2. Why is 2? Omega by omega 0 is 2. I did this maths for you. I have this शेबेशायर फंक्शन, यहाँ लिखा हुआ है आपको फिर से. I substituted this value in this Cn square is 10 to power 4 minus 1 upon this. I यहाँ से calculate किया, Cn2 निकाला. Why I am calculating? I use this expression, substitute attenuation and evaluate the value of Cn square 2. Is that correct? आपको 40 dB चाहिए था, transfer function should reduce by 40 dB, so 10 to power minus 4. This is 1 plus, why ये स्क्वायर क्यों किया है मैंने, वो अंडर रूट था इसलिए इधर स्क्वायर कर दिया मैंने एक्सप्रेशन को. तो 1 plus एप्सिलॉन स्क्वायर इनटू द शेबेशायर फंक्शन स्क्वायर at 2 at omega by omega 0 equal to 2. So I went to evaluate this value from this. I know this, I know this. I calculate Cn square 2 to be 3.86 into 10 to power 4. That means Cn, the Shebeshaire function at omega equal to twice omega 0 is 3 under root this into 10 to the power 2. This function, iski value है 196.5 and the Shebeshaire function is cos h. Why I am using cos h? Omega greater than omega 0. This is Cn2 is 3.86, this is 196.5 equal to cos h, n cos h inverse 2. यदि इसका फंक्शन सॉल्व किया so n becomes 4.53. इज दैट क्लियर? कितना सेक्शन लगे आपके हिसाब से, कितने पोल्स लगे? 5. बटरवर्थ में कितने लगे थे? 7. प्राइस क्या दिया? 1 dB का रिपल एक्सेप्ट कर लिया. इज दैट करेक्ट? 1 dB का रिपल एक्सेप्ट कर लिया. यदि हाफ dB का करते तो क्या होता? थोड़ा सा 5 का बजाय 6 आ सकता था. एप्सिलॉन डिनोमिनेटर में ना, और 0.30 वैल्यू है उसकी, तो इसका मतलब n सेक्शन थोड़ा सा नंबर थोड़ा और ऊपर हो जाता. पर यदि वो 7 हो गया तो देयर इज नो पॉइंट इन देन यूजिंग शेबेशायर फिल्टर. इज दैट क्लियर? तो शेबेशायर कब यूज करते हैं मालूम है क्या? जब लार्जर बहुत शार्पर चाहिए रहता है 60 dB और दिस, तब जरूर शेबेशायर यूज करें. क्यों? Because corresponding Butterworth may require 12-15 larger number, Shebeshaire may require 8-9-10, so 4-5 section का फर्क पड़ता है. So जब larger sharper falls आप देख रहे हैं 60 dB, 80 dB sharp, then you better use Shebeshaire filters. If you are looking relatively 40 dB or something of that kind, you may as well use Butterworth with no ripple around. So ये थोड़ा सा चॉइस करना पड़ता है कि कितना एक्यूरेसी, कितना पास बैंड, कितना रिपल एक्सेप्टेड है, इस हिसाब से यू कैन डिसाइड. इज दैट करेक्ट? दिस इज व्हाट द डिजाइन ऑफ ए फिल्टर इज ऑल अबाउट. इज दैट करेक्ट? सो सबसे पहले आपको क्या बताएंगे? वी विल जस्ट टेल यू दैट आई वांट ए एटेन्यूएशन एट दिस फ्रीक्वेंसी सो मच. ओके, देन यू विल यूज बोथ फंक्शंस. इज दैट करेक्ट? एंड इवैल्यूएट हाउ मच n that is giving, how much n this is giving, for both values of gamma also, half dB as well as 1 dB, and then figure out which one you should choose. I first take, once I am given at this frequency, this is the attenuation I am asking for you, then you say okay, I will use Shebeshaire formula for both gamma equal to half dB and gamma equal to 1 dB. I will also use Butterworth function, find for ripple 0 how much is n. If n is much lower in Butterworth for the you want, then you need not go for Chebyshev at all, okay. But let us say you are getting Chebyshev much smaller than the Butterworth, for even for a 1 dB ripple you better go for it, is that clear? So the choice of kind of function choose and kind of sections you can use is decided by what specifications filter is asking from, is that correct? So is the word clear why I said design, because what will be specified to us, so many dBs down at this is specified, okay. Then we calculated what normally what we should do, okay, n is 5, substitute, get the value, say okay it will give 43 dB. This is not what we have to do. Someone will tell this is the filter I want, this should do like this. Then I should reverse way go and figure out what should I do. Should I use Chebyshev with half dB ripple or 1 dB ripple, or should I use Butterworth? Okay. You have a choice. So calculate with this kind of thing all three and choose whichever cost wise you feel is cheaper and acceptable, use that. This is what the design is all about. So this course I am trying to again and again bring to your notice that at the end of the day we are not analyzing things, but to do this I must know the function themselves, I must know how we are using them. So analysis is only required to know what options I hold, okay, because at the end I will be given by customer, as we say all designs are custom designs. What does that custom design means? The customer specifies this is what I want. So you go to a shop and you make a choice, I want this, I don't want this. So that's the choice a customer has. Manufacturer has no choice. He has to provide, he say okay you want this cost itna hai. You want this, oh it is even costlier. Ek TV hai, LCD hai, 39,000 ka bhi hai, 65,000 ka bhi hai, LED karo to 75, plasma karo to la. What you want, yeah, money is accordingly, okay. तो यदि आप टॉलरेट करते हैं रिपल, ठीक है सस्ते में दे दें. So that's the trick all designers follow. Please remember my attempt in this course all through was to bring to your notice that the designers, how designers look at the theory which we do, okay. Always measured 1 because Butterworth people believe that epsilon 1 के ऊपर flatness करीब 0 है, gamma is almost 0 dB. Flatness is related to ripple. So gamma is higher, which means epsilon is higher means you are closer to the kind of ripples you are looking for, okay. No, in so ripple magnitude if it is given, then you say okay if maximally flat filters gives much lower ripple anyway, isn't it? And it still gives you lower section, so why do you want to have a higher ripple with a lower, you already got a lower value of that. The choice is yours, you can still use Chebyshev, but if I can give equivalent sections or around the same sections as 5 or 6 hoga, so I may actually go for 6. Because then I say I don't have to worry about, because if I am giving you 0 dB ripple, which is anyway better than half dB ripple you are asking for, which was your this. So you can, that is the maximum allowed to you, below anyway is allowed, is that correct? So if you say that your 6 section and 5 section you have to make a choice, you may better make a choice of 6 because you say okay ripple is now no more there. See the choice is something like this, if I say half dB ripple, then I say okay it is roughly equal to that 10 to the power gain by 10 minus 1, you evaluate epsilon from there. So that value will tell you what is the flatness on the gain function you want, okay. That flatness means ripple on that. The flat A max जो है वो कितना उसके ऊपर overreading करना चाहते हैं आप, that is your value of epsilon you are choosing. If you say 0, fine, okay, ripple 0, fine, so epsilon is 1 for that, so use 1. They are always related by same function, okay, is that okay? Okay, here is, I have just copied it, xeroxed it rather. This is the order of polynomial, Butterworth polynomial 1, 2, 3, 4, 5, 6, 7, 8. This is normalized polynomial BNS. If n 1 है the function which I am realizing in Butterworth is s plus 1, that is a pole, s plus 1. If n is equal to 2, I am realizing s square plus root 2s plus 1, okay. If n is equal to 3, it is s plus 1 times s square plus s plus 1. If n is 4, two s square terms will appear. 4 means 4 poles, so s square plus s plus into s square plus s plus something. So 4 poles, is that correct? These are number of poles. 5 means s plus 1 into 2 s square bracketed term, is that correct? 5 poles. So you can see whenever there is a odd number of poles, there will be s plus 1 single pole ऐसा निकालना है. और वो कौन सा इसमें और इसमें फर्क क्या है? एस स्क्वायर रूट 2s प्लस 1 और s प्लस 1 में एक्चुअली पोल में क्या डिफरेंस? एक a स्क्वायर, थोड़ा सा एक्सप्रेशन सोचो, जब भी ये होगा ये कॉन्जुगेट पोल्स देंगे एस स्क्वायर टर्म्स वाले, जबकि ये जो s प्लस 1 कौन सा पोल देगा? रियल एक्सिस पे आने वाला है तो उसको बोलते हैं रियल पोल, इज दैट करेक्ट? The other two always will be a conjugate poles, whereas this will be a real pole, okay. So what should I have to realize? I must be able to realize the conjugate poles as well as a real pole. So if I have a circuit which realizes a single pole which is real and also can replicate a s square s kind of terms, then I am having a transfer function. So how many, if this is this third one, so what is the kind of function I am saying? 1 upon s plus 1 into s square plus root s plus 1. This is the kind of function I am having from the Butterworth, is that correct? Each I should be able to realize now, okay. What is the method I said? If you have a 3 functions, 1 upon s plus 1 plus 1 upon s plus b, 1 upon s plus, so what, there can be 3 transfer functions, this into this into this. So I realize first function and output of that I give it to the input of the next. I have product of the 2 now, output of I give it to the third stage, the product of the third will also appear. So all that I do is, each is now clear is what is the section? Section means realization of a single pole, okay. So 1 upon s plus 1 is one transfer function, into 1 upon s plus something is second transfer function. So I realize individually each pole, is that clear? And since I can realize a pole, I have just shown you the theory earlier, फिल्टर का एक पोल तो बनाना सबसे RC, एक RC से या 2R से आप हमेशा ऐसे फंक्शंस 2R RC से क्या फंक्शन बना सकते हैं? 2R और 2C से एस स्क्वायर टर्म्स आ सकते हैं, एक RC से सिंगल पोल आ सकता है. So we should be able to then realize any number of such sections in series of that, is that correct? So n7 हुआ है, understood? 7 means there will be 7 sections of realizing individual poles, is that correct? That means there are so many series combinations are going on to realize that function. And as he said, the penalty essentially is the power. Larger the sections, each will draw power, okay. Okay. So once you get, either you are going for Chebyshev or going for Butterworth, you are decided this is the function you implement. This is known that I will, if it is a Chebyshev function, I will implement this. If it is a Butterworth, I will implement that. Is that clear? Is that clear? So that is the, I have started with As upon Bs is the transfer function, As, all pole As is 0, constant. So I am actually realizing that function, which is the transfer function I said. Is that clear? Okay. ये आप बुक में देखिए, सेड्रा स्मिथ में पूरे टेबल्स हैं. If I am asking you to design something, I will provide you this table. Is that clear? I will, you don't have to remember, I will provide you this table. Only thing is that n you must get it and choose among them which function to realize. Is that correct? So how to design a filter? I repeat, given the spec, find which filter and which order and choose expression from here or there. This is for half dB, this is for 1 dB, okay. इससे ज़्यादा की जरूरत नहीं पड़ती, so don't go. Because it is a much larger, then it is worse, okay. Okay. This is, as I say, please don't have to remember anything. This is just to show you s plus something. You can see the functions are not very different. Here only thing it was s plus 1, here it is s plus 2.863. The next term is s square 1.425s. This is derived from the Shibesha and Butterworth functions, these values. Okay. So please look into book, or rather, as I said, just for the heck of it, I just say you these are the functions I am going to realize. This is called Sallen and Key low pass section. Okay. Now this word section is clear. How many poles this is going to realize? Each of them, inverting or non-inverting? 2 poles. So कौन सा term implement हो रहा है? 1 upon s square plus something, and that constant जो है 1.425 है, वो कहाँ से आने वाले हैं? कि R1, R2, C1, C2 के values से आने वाले हैं. Is that clear? The constants which you have derived expression, you have got from functions, have to be now implemented through R1, C1, R2, C2 values. Okay. But that is normally taken higher than this. You can see now your gain is now reduced. So वो तो बहुत आगे है, तो आपको 0 GVW बहुत आगे है, का इतना problem. You have a point. This is one. 2 pole theory में n is equal to 2 is there 2 poles. So 1 s square sections. Is that correct? n is equal to 5 means 1 upon s plus 1 into s square का एक bracket और उसका और एक s square का और एक bracket. 3 sections. s square के लिए एक section ये हो गया ना, 4 है तो 2 ही section लगेंगे, और यदि 5 हुआ तो एक s plus 1 के लिए भी एक section लगेगा, वो दिखाता हूँ मैं आपको. हाँ, वो कास्केड कर दें. इसका आउटपुट नेक्स्ट के ऊपर ऐसा ही सेक्शन जो नेक्स्ट के लिए बना रहे हैं, प्लीज टेक इट दिस वैल्यू जस्ट टू गिव एन आइडिया. लेट्स टेक आई एम डूइंग बटरवर्थ, n इज इक्वल टू 4 और 5. तो एक तो s प्लस 1 है, वो अलग से बनाना है. 2 टर्म है s स्क्वायर प्लस 0.618s प्लस 1, एक ये रियलाइज होना है. दूसरा s स्क्वायर प्लस 1.618s प्लस 1, ये दूसरा रियलाइज होना है. तो ये जो एस स्क्वायर टर्म वाला ये एक सेलन की का सेक्शन है जो अभी दिखाया. अभी एक और सेक्शन हमको देना, ये 2 सेक्शन लगेंगे इन्हें 5 के लिए. इज दैट करेक्ट? ईच एस स्क्वायर टर्म कैन बी रियलाइज्ड बाय 1 सेक्शन. तो यू रिक्वायर 2 सेक्शन फॉर 2 एस स्क्वायर टर्म्स. द थर्ड कौन सा है? रियल पोल चाहिए, तो उसके लिए एक और सेक्शन लगेगा जो हम लास्ट में देंगे, अभी दिखाते हैं. इज दैट क्लियर? सो गिवन द ट्रांसफर फंक्शन, वंस यू मेक ए चॉइस, you can actually start realizing using Sallen keys. Okay. तो 5 के लिए कितने सेक्शन लगेंगे? 3. 6 के लिए 3 ही लगेंगे. Is that clear? अभी मैंने पीछे बार आपको एक जवाब दिया था कि 5 और 6 हो तो 6 यहाँ ले सकते हो, क्योंकि सेक्शन के हिसाब से 3 सेक्शन ही लगते. Is that okay function wise? Is that clear? n इज द सेक्शन, इसलिए मैं बोला था कि मैंने गलत बोल दिया शायद. n उससे थोड़ा सा कंफ्यूजन हो गया. एस स्क्वायर एक सेक्शन से आता है, यानी 2 पोल्स एक ही सेक्शन से मिलते हैं. n इज द नंबर ऑफ पोल्स, 5 है तो 5 पोल हैं, पर 2 पोल एक ही सेक्शन से बनाए जा सकते. इज दैट क्लियर? सो सेक्शन वाइज, आई एम सॉरी, आई मेड अ मिस्टेक. सेक्शन वाइज एस स्क्वायर टर्म कैन बी रियलाइज्ड बाय 1 सेक्शन. अनदर एस स्क्वायर टर्म होगा तो एक और सेक्शन, और एक एस प्लस टाइप का होगा तो एक तीसरा सेक्शन. इज दैट करेक्ट? तो 3 सेक्शन. आई विल शो यू एन एग्जांपल. अभी आप सोचो कि जो आपका फाइनल ट्रांसफर फंक्शन प्लस है आना है या माइनस आना है, वैसा उसके हिसाब से साइन लगाओ उसके. ओके. एक शायद इन्वर्टिंग होगा तो दूसरा नॉन इन्वर्टिंग. ओके. ओके. अभी मैंने आपको बोला कि आई नीड कॉन्जुगेट पोल, तो एस स्क्वायर्स के वाले थे, बट देयर मे बी अ रियल पोल रिक्वायरमेंट. इज दैट करेक्ट? रियल पोल रिक्वायरमेंट. तो हियर इज ए सिंगल रियल पोल. आपको क्या बोला कि आरसी है तो लोड हो जाएगा? नहीं, आरसी इज दैट द आउट, दिस इज द फिल्टर. इनपुट इज नॉट लोडिंग, इनपुट इज कमिंग हियर विथ हाई इम्पीडेंस ऑन दैट, सो इट इज नॉट गेटिंग लोडेड बाय दिस. यदि इसे और ड्राइव करना है कहीं तो वहां भी एक बफर डालना पड़ेगा, वहां भी एक बफर डालना पड़ेगा. सिंगल पोल मिला, ये 1/1 प्लस आरसी है, एक सिंगल पोल मिल गया आपको. 1/RC पर एक पोल है आपका. यदि इन्वर्टिंग चाहते हैं तो नॉर्मल R2 R1 लगाइए तो एक एडिशनल टर्म आ जाएगी। अच्छा, इसको R2 बाय R1 को हटाना है तो क्या करना चाहिए, इक्वल कर दो, R2 इज इक्वल टू R1, तो 1 हो जाएगा, ठीक है। If you want a gain, fine. If you don't want, put R2 is equal to R1, so that will become 1 upon S by 1 upon RC with a minus sign. Is that clear? Choice of R are yours, so you can always get rid of R's. Okay. So this is called creation of a real pole. Is that correct? Real single pole. Why it is called real? Again and again I am telling you, because ये S is equal to minus real life, real value पे जा रहा है, otherwise S square term हमेशा conjugate poles लेके आएंगे. Okay. So this finishes the filters. बैंड पास कैसे बनाएंगे, एक लो पास बनाएंगे उसका ओमेगा 0 निश्चित करेंगे, एक हाई पास बनाएंगे उसका ओमेगा। अच्छा, इसका यदि हाई पास बनाना है तो क्या करना चाहिए, आर और सी को उल्टे करोगे तो वो हाई पास हो जाता है। इज दैट करेक्ट? रिप्लेस आर बाय सी, सी बाय आर। ओके, एक्सेप्ट द फीडबैक। वो R1 R2 को सी मत कर देना। इफ यू सी द फंक्शन, अरे अभी देखा नहीं क्या फिगर मेरी, ये आर और ये सी है, बस ये बोला ना इनको मत करना, ये फीडबैक है, वो मत हटाना। ये सी आर, ओके, so you'll get that high pass. Is that okay? So I have now, I can create a band pass, band reject, low pass, high pass using Salanki filter sections, okay, either using Chebyshev coins or using this. मैंने एक सबसे पहले आपको एक फिल्टर का एक जनरलाइज नेटवर्क दिया था। इफ यू सी इट, इट इज ट्राइंग टू डू द सेम थिंग। इज दैट क्लियर? एक जनरलाइज आपको मैंने नेटवर्क दिखाया था ओपैम्प के साथ, वो बेसिकली यही है वो। ओके, इज दैट क्लियर टू यू? सो देयर आई डिड नॉट नेम दैट एज ए Salanki सेक्शन, बट इट इज एसेंशियली ए Salanki सेक्शन। इज दैट क्लियर? आपने देखा ना, एक जनरलाइज नेटवर्क दिया आपको मैंने, वही यूज कर सकते, वही है एक्चुअली। ओके, यहाँ थोड़ा सा आर सी दिखाया, वहाँ G1 G2 लिख दिए थे, थोड़ा कंफ्यूजन किया, बट सेम है। यस, आप इसका थोड़ा सा एनालिसिस करो और आपको मिल सकता है। एक को अश्यूम करते हैं, बाकी सब प्रोपोर्शनली निकाल। ओके, एक सी को लेते हैं, उसके प्रोपोर्शन सबको निकाल देते हैं, क्योंकि वो रेशो में मिलेंगे आपको। ओके, सो दिस फिनिशेस फिल्टर्स। एक ऐसा ही मुझे स्ट्राइक किया थोड़ा सा, प्लीज टेक इट। मैं आज थोड़ा सा सेड्रा स्मिथ देख रहा था, तो आई फिगर्ड आउट this something which I didn't tell you, so I thought maybe quickly I will tell you something more interesting what they did for stability. So that's why I named it revisit. Okay. What is the way I told you to find the stability of a amplifier? कि आप AOL निकालो, बीटा निकालो, AOL बीटा बनाओ और लूप गेन प्लॉट करो। ओके, और लूप गेन में उसका फेज निकालो इसके ऊपर, और यदि वो गेन मार्जिन यदि पॉजिटिव रह गया जबकि फेज 180 डिग्री क्रॉस हो गया है तो अनस्टेबल है, वो आपको बताया। ये करने के लिए भी इतनी भी जरूरत नहीं। दिस इज वेरी इंटरेस्टिंग, मैथ्स हैज बीन डन बाय सेड्रा स्मिथ एंड आई थॉट यू कैन रीड दैट मोर डिटेल। This is just to give his idea, which is fantastic. So I should have also, this we do in other method, but I hear this. This is the loop gain is A beta. Is that clear? How can I write A beta? A upon 1 by beta. A beta can be written as A upon 1 by beta. I take log. So 20 log A beta is nothing but loop gain in dBs, which can be written as 20 log AOL minus 20 log 1 upon beta. तो अभी हम क्या कह रहे हैं कि you don't find 20 log A beta at all, loop gain निकालो ही मत। Plot AOL versus omega, Bode plot for open loop amplifier. Is that point clear? Don't get A beta, just plot Bode for magnitude of AOL versus omega and phase corresponding. Is that clear? Then I want to subtract, this is that 20 log A means Bode plot of that. Beta is constant in this case. So 20 log 1 upon beta is a constant value. Okay. आप बीटा जरूर निकालो, वो तो आप निकालोगे ना. So 20 log 1 upon बीटा का एक लाइन बनाओ यहाँ पर, कितने dB है वो. This is our, without this is our AOL transfer function. Okay. नॉर्मल ओपन लूप का पोल्स हैं जितने भी 3, 4 जितने भी होंगे. यहाँ पर मैंने एक लाइन लगाई ऐसी विच हैज द वैल्यू ऑफ 20 log 1 by बीटा. ओके, इसकी जो भी वैल्यू है यहाँ लगा दी मैंने, इस पर एक लाइन खींच दी. दिस इज अवर AOL, दिस इज 20 log 1 by बीटा, दिस इज 20 log A. तो ये डिफरेंस क्या है? लूप गेन. यहां पर कितनी वैल्यू उसकी? लूप गेन की वैल्यू कितनी है? 0 dB डिफरेंस है, यानी कितनी वैल्यू? 1. नहीं तो भी हम बीटा फेज कहाँ निकाल रहे थे? जबकि लूप गेन 1 है वहां फेज देख रहे थे ना. नॉर्मल मेथड में मैंने क्या बोला? ए बीटा वर्सेस ओमेगा प्लॉट करो और जहां वो 1 होता है वहां फेज देखो. अब मैंने कहा कि यहां तो लूप गेन की वैल्यू 1 है ही ना, इसका फेज ढूंढो कितना है फेज डायग्राम पर. यदि ये 180 से कम है तो स्टेबल है, क्रॉस कर गया -220 या -185 हो गया तो वो अनस्टेबल है. तो जैसा ही आपने बीटा फिक्स किया, आप बीटा यहाँ अलग अलग लाइन बना सकते हैं. इज दैट पॉइंट क्लियर? फॉर डिफरेंट फीडबैक्स बीटा वैल्यूज आई कैन हैव डिफरेंट स्ट्रेट लाइन्स, विच मीन्स द कट ऑफ पॉइंट विल चेंज. इज दैट करेक्ट? इफ द कट ऑफ पॉइंट चेंज, यहाँ क्या स्टेबल लगता है क्या? समझो ये 160 dB है, 160 डिग्री माइनस है यहाँ, तो स्टेबल है क्या? ये स्टेबल है. यदि आप नीचे जाएंगे, समझो यहाँ रखेंगे, तो हो सकता है यहाँ पर जो पोल होगा वो 180 क्रॉस कर गया होगा. तो यदि 1/20 log 1 upon बीटा 50 है, समझो 50 dB है, ये 100 dB है, तो 50 dB जब नीचे आए आप, तो फेस कितना कर गया क्रॉस? 180 क्रॉस कर गया. तो इस फीडबैक के लिए सिस्टम अनस्टेबल हो गया. ओके, इस फीडबैक के लिए सिस्टम अनस्टेबल हो गया. तो चॉइस ऑफ बीटा कैन बी एक्चुअली प्रीडिफाइंड. कितना बीटा ले सकते हैं आप कि सो दैट रिमेन सिस्टम रिमेन स्टेबल. इज दैट करेक्ट? AOL, नो, प्लॉट द फेज ऑफ AOL. यही मैं बता रहा हूं, नॉर्मल एम्पलीफायर का बोर्डे प्लॉट करो. इज दैट करेक्ट? All that I am saying, what is this point? Loop gain 1, but phase तो वही है उसका जो नीचे है. यदि वो 180 क्रॉस कर रहा है, -180 से अबव हो रहा है, तो सिस्टम अनस्टेबल हो रहा है. यदि उसके नीचे रह रहा है तो सिस्टम स्टेबल है. सो एक गिवन ट्रांसफर फंक्शन जैसे ही आप ओपन लूप का इक्विवेलेंट बनाएंगे, उसका ही बोर्डे प्लॉट कर दीजिए. बीटा का वैल्यू प्लॉट करिए और नीचे देखिए फेज कितना है, स्टेबल अनस्टेबल वहीं पता लग जाएगा. इज दैट क्लियर? If this is 1, this is 0. A beta 1 is 20 log, that is 0. That means these must be equal. At this point, both are equal. Okay. Given feedback network amplifier, first make AOL, जो तो आपको बताया कि open loop with loading चाहिए आपको, वो AOL S निकाल लो आप, उसको बोर्डे प्लॉट बनाओ उसका. अब जो फीडबैक दे रहे हो बीटा नेटवर्क का, वो बीटा निकाल लो. 20 log 1 upon बीटा की वैल्यू निकाल लो. जो AOL का ट्रांसफर फंक्शन का बोर्डे प्लॉट था, उसमें ये 20 log 1 upon बीटा की एक लाइन लगाओ. वो तो कांस्टेंट है ना, बीटा कांस्टेंट है. वो जहां भी इंटरसेक्ट कर रही है, दैट मीन्स दिस वैल्यू इज इक्वल टू दिस वैल्यू. दैट मीन्स ए लूप गेन इज 1. ओके, सो दिस इज द पॉइंट वेयर लूप गेन इज 1. एंड वी सेड इन स्टेबिलिटी, वेरेवर लूप गेन बिकम्स 1, फाइंड द फेज. ओके, that is phase margin should be plus 180 से नीचे रहना चाहिए. यदि वो 160 दिखा रहा है आपको फेज प्लॉट पे, तो वो स्टेबल है. पर समझो आपने बीटा एक्स्ट्रा बढ़ाया, ये किया, चेंज किया, so that 20 log 1 beta is lower value now, that is feedback is larger, let's say per se. अब यहाँ तो 2-3 पोल होंगे, कहीं भी होंगे, तो ये पॉइंट आ गया आपके पास जहां पर these are equal, that is loop gain is 1. यहां पर फेज ढूंढो. यदि वो 180 क्रॉस कर चुका है तो सिस्टम अनस्टेबल हो गया. कहाँ पर ये जीरो मार्जिन होगा? You'll have to find when they are equal, find the value of such value of beta where the phase is 180 degree. At that point देखो, समझो ये 180 का पॉइंट है, समझो यहाँ पर, सब यहाँ पर ये 180 आता है फेज, तो ये वैल्यू जो है इसका ये 20 log 1 अपॉन बीटा, इससे जो बीटा वैल्यू आएगा that is the minimum beta you must use so that the at least stability start हो रहा है. उससे ऊपर जाना है आपको, उससे नीचे रह गए तो अनस्टेबल हो जाए. This method has been provided as an alternate method in Cedra Smith book. Alternate लिखा है उन्होंने, इसलिए मैंने पढ़ा भी actually. तो आप एक बार देख लो, because this is much easier in my opinion. But if you are using my earlier technique of finding loop gain and plotting, is nothing wrong. Anyway आधा काम तो कर ही रहे हैं, A भी निकाल रहे हैं, बीटा भी निकाल रहे हैं, प्रोडक्ट भी निकाल सकते हैं, उसका फेज भी निकाल सकते हैं. But this is easier way of doing it. Is that clear? This is what they have suggested and I thought you should know. Okay. This next analog block which is required by each and every one of us in our system is oscillators. Okay. Once I said, gave you some joke that whenever I design an amplifier, it oscillates, and whenever I design an oscillate, it amplifies or rather attenuates. Okay, वो filter जैसा काम करने लगता है. तो इसका मतलब oscillator का criteria कुछ होना चाहिए, वो वहीं पर वो exact oscillate करता है. So let's see what is that criteria. This is our standard feedback network. The only difference now I am saying compared to the earlier feedback network. क्या फर्क दिखा रहा हूँ मैं यहाँ पर? Anyone? You know, X is input and X is output. That's fine. ये क्या दिखाया मैंने? बीटा एस, पहले क्या लिया था एम्पलीफायर के साथ? बीटा इज कांस्टेंट. ओके, नाउ आई से बीटा कैन बी ए फंक्शन ऑफ फ्रीक्वेंसी. व्हाट डज दैट मीन? बीटा में क्या नेटवर्क क्या हो सकता है अब यदि फ्रीक्वेंसी टर्म आ रही है तो? और इंडक्टेंस कुछ भी हो सकता है. तो अभी नाउ यू रियलाइज दैट यू आर सीन ऑसिलेटर्स में टैंक सर्किट लगाते हैं, एल एंड सी या आर एंड सी. This is exactly what it means. The beta network has now frequency dependence. All amplifiers we avoid that. We want to, अभी दिखाया ना एक फिगर, बीटा कांस्टेंट है, यहाँ बीटा frequency dependent है. We already said loop gain Ts or in some book Ls, As into beta S. Hence if 1 plus A beta is 0 or A beta is minus 1, ट्रांसफर फंक्शन की वैल्यू कितनी होगी? इन्फिनिट. इफ ए बीटा प्लस 1 इज 0, न्यू डिनोमिनेटर इज 0, ट्रांसफर फंक्शन हैज अ वैल्यू ऑफ इन्फिनिट. इज दैट क्लियर? व्हाट डज दैट मीन इन एम्पलीफायर? V0 by Vn is infinite. What does that mean? Without having input Vn, I can create V0. Is that correct? V0 by 0 is infinite. Is that correct? So without having an input, I have an output now. Is that clear? By using a feedback theory which I said. Okay. Is that point clear? Without having any input, what is gain? V0 by Vn. Okay. If I say gain is infinite, which means without input I have output. Is that clear? This term without having actual input provided, I actually can get constant value of V0 is called oscillator. Okay. The condition will lead to oscillations. Okay. Is the principle clear to you? So what we are saying, I pass some input to A which becomes X0, beta of that I return it to Xi, and if it is such that this adds to this, then increase X0. Afterwards, if I at a certain value, even if I remove Xi, it will still start feeding some input, output, वो आपस में loop में घूमता रहे. When that occurs, then we say we are having a oscillations. Because initially, that means initially कहीं तो भी Xi होना जरूरी है. Is that clear? What this Xi will be initially? कहाँ से आएगा? नो एक्चुअली इन ऑसिलेटर यू नेवर गिव एनी इनपुट ना, सो कैसे स्टार्ट होता है नॉइज. सो लिटिल बिट ऑफ नॉइज can start oscillations in no, it will grow to a standard frequency oscillators. Is that correct? So that is why no real inputs are actually required to start oscillations. As soon as you switch on the power supply, a pulse आता है. आपको कुछ भी नहीं करना पड़ेगा. So there is a person called Mr. Barkhausen. He suggested a criteria, okay, which will give a unified oscillations. अभी क्या बोला, लूप गेन -1 होना चाहिए बोला ना आपको, तब वो इन्फिनिट हो रहा है ट्रांसफर फंक्शन. So at any given frequency, say f1, the magnitude of this transfer function is 2 pi j f1 is equal to 1 magnitude. And what is its phase? Because of its -1 value, minus 180 degree. Is that correct? Minus 180 degree. So what Mr. Barkhausen says that at any frequency, if the magnitude of this loop gain is unity and its phase is 180 degree, then you will have oscillations. This is one possible condition. अभी फिजिक्स क्या बोलते हैं हम लोग? Let's say A is a 180 degree phase out, इनपुट to आउटपुट गेन जो है 180 डिग्री देता है, माइनस GM लिखते हैं ना, एक 180 डिग्री आया, 180 डिग्री इससे भी आया आपके पास, तो कितना टोटल फेज हुआ? 360 और 0. इज दैट करेक्ट? तो जो रिटर्न सिग्नल मिला आपको वो कितना पहुंचा? इन फेज टू द इनपुट. इज दैट करेक्ट? तो थोड़ा सा इनपुट मिला, वो थोड़ा आउटपुट पे गया, रिटर्न उसने इन फेज फिर इनपुट को दिया, ओके, उससे फिर बढ़ा, उसका ज्यादा फीडबैक आके फिर मिला आपको, उसके बाद आप इनपुट हटा लो, अभी नॉइज नहीं भी चाहिए, वो फिर थोड़ी देर में एक जाएगा, एक कहीं कंडीशन पे जबकि जो मैक्सिमम बीटा अलाउ कर सकता है, जो मैक्सिमम आउटपुट आपको मिल सकता है वहां स्टेबल हो जाए इस फ्रीक्वेंसी. इज दैट करेक्ट? नाउ दिस इज व्हाट ऑसिलेटर इज ट्राइंग टू से. दिस क्राइटेरिया सेज द मैग्नीट्यूड ऑफ लूप गेन एट अ गिवन फ्रीक्वेंसी इफ इट इज 1 यूनिटी and its corresponding phase is minus 180 degree, then oscillation at f1 can be seen. इसका एक alternative system भी हो सकता है. If you take the transfer function here and you say its real value is -1 and imaginary value is 0, even then this condition is satisfied. Is that clear to you? Please take it, maths में दोनों हो सकता है, मैग्नीट्यूड 180 डिग्री और 1 हो सकता है, या इसमें ट्रांसफर फंक्शन में इमेजिनरी वैल्यू 0 कर दिया, दैट इज हाउ मच इज द फेज? 0 फेज. फेयर एनफ, ओके, बट द इमेजिनरी पार्ट इज 0 and the magnitude is 1, which is also is you have a situation in which system may become unstable or oscillatory. This is what essentially Barkhausen suggested. Now in real life, how do I achieve that? तो इसका जो मैंने स्टेटमेंट दिया वो लिख लो, वो बुक में से लिया गया है. That is to say, oscillation conditions will be phase shift through amplifier and feedback network must be such that it is either 0 or 360 degree. That is, the feedback return is in phase with the input and the magnitude of A beta is 1, then you have a condition of oscillation called Barkhausen criteria. Is that 360 0, 180 minus 180, minus 180 minus 180, which is also 0. एक एम्पलीफायर का हमेशा 180 आया ना, ए का ए बीटा इज ओके, बट देर इज जो रिटर्न होके आया, ए बीटा यानी रिटर्न मिला जो आपको फीडबैक पर, उसका 180 और 180 एम्पलीफायर से आया, तो 180 प्लस 1. assumption is that amplifier gives you 180 degree. Is that correct? Yes. So this criteria is called Barkhausen criteria. So अभी जो आपको जो सर्किट बनाएंगे उसमें क्या एडजस्ट करना है कि आउटपुट से रिटर्न जो इनपुट पे जाएगा उसका फेज कितना होना चाहिए? 180 डिग्री. एक एम्पलीफायर का 180 और 180 फीडबैक से दिया तो इनपुट में 0 डिग्री फेज पे वापस आ गया। अभी देखो थोड़ा सा आउटपुट आप भी देख लीजिए। एक एम्पलीफायर है, नॉन इन्वर्टिंग है, ये माइनस आया, इस आरसी नेटवर्क को ये लेके आया तो इसको इन फेज कंपोनेंट 180 यहाँ से आया, 180 यहाँ से आया, टोटल essentially saying feedback is giving 180, this is giving 180, return path is 0 degree. एम्पलीफायर का 180, फीडबैक नेटवर्क का 180, टोटल 360 और 0 whatever you call it. ऐसा यदि कंडीशन आपने एडजस्ट कर लिया, इसको बोलते हैं फेज शिफ्ट ऑसिलेटर. व्हाई इट इज कॉल्ड फेज शिफ्ट? 180 phase is shifted by another 180 to create a oscillatory conditions. ये 3 RC दिखा रहे हैं हम यहाँ पर, तो कितना फेज होना चाहिए हर एक में? 180 करना है तो 60 डिग्री. सो इन RC कांस्टेंट को टाइम कांस्टेंट का ऐसा बनाओ कि इसका फेज ईच का सेक्शन का 60 डिग्री हो जाए, तो 60 प्लस 60 प्लस 60 180 हो गया आपका फेज शिफ्ट. ओके, is that clear? We'll come back to it again, but I just want to show what is Barkhausen's criteria. Okay. How is it different from this case? This condition is start of instability in amplifier. Is that point clear? This was the point, अभी जो मैंने दिखाया, this was the point A beta equal to -1. वहाँ पर अनस्टेबल होना शुरू हुआ ना, इंस्टेबिलिटी आई एम्पलीफायर में. तब हमने कहा कि ऐसा फीडबैक रखो कि वो उसके पहले 180 हो ही ना. फिर कैसे करोगे? 180 होते हमको पता है फेज में जाने वाला है. अब ये ट्रिक कर रहे कि नहीं, उसको 180 ही करना है, एग्जैक्टली करना है. तो इज दैट नाउ पॉइंट क्लियर व्हाई समटाइम्स एम्पलीफायर डू नॉट बिहेव लाइक एम्पलीफायर्स and oscillators do not, because their phase may not become exactly 180, then it will not, it will थोड़े देर ग्रो होके डाउन डाई हो जाते हैं. तो ऑसिलेटर ऑसिलेट नहीं कर पाते और एम्पलीफाई के बजाय ऑसिलेटर हो जाते हैं या ग्रोइंग फंक्शंस या डैम्पिंग हो जाते हैं. दैट इज व्हाट द स्टेबिलिटी थ्योरी इज सजेस्टिंग, दैट यू मस्ट गेट योर फेज एंड मैग्नीट्यूड exact. Okay, is that clear to you? This is what essentially Barkhausen suggested. Based on that, we'll have some 3, 4, 5 kinds of this. Then we will start moving from after few oscillators. I'll not go all of them. Next time I'll start few of them, and then I'll start for you most important part in this, A to D and D to A converters. क्यों हम वो important है हमारे लिए? Because दुनिया तो डिजिटल है, दुनिया तो डिजिटल है. Thank you.